Good afternoon in Europe, good morning in North America, and hello to everybody. FlexSNG is a Horizon Europe project now nearing its end. It's all about developing a large capacity biomass to bioSNG process using gasification-methanation. Besides the many technology challenges of such processes, especially considering different biomass feedstocks, which has been addressed by VTT in the project to TRL5 in their pilot plant. This, like many similar large capacity biofuel biorefineries, is techno-economically challenged. The Canadian contingent of the FlexSNG team had the opportunity to look at various systems aspects of FlexSNG. The program was designed first to quantify strengths and weaknesses of the case studies that were considered in Europe and in Canada. And number two, to seek solutions that would improve the techno-economics of the process. So we're thrilled to have this opportunity to speak to you today, and we have been thrilled to be part of the FlexSNG team over the last 3.5 years. We're only presenting some of the overall work that we've accomplished, and we haven't even begun to talk about the significant body of work that's been addressed by CERT for modeling the results, the techno-economics, the basic results, and the life cycle assessment. But hopefully we've selected the most interesting aspects to address for you today. We didn't want to report in some way during the webinar, but rather inspire our community by some of the systems analytics that we've used, really targeting large capacity biofuel biorefineries. So please enjoy the presentation, starting with that of my dear colleague, Professor Michael Ronquist of Université Laval, who will formally introduce the webinar. Just a quick reminder to please put your questions only in the Q&A tab in the Zoom. So thank you, enjoy the seminar, and over to you, Michael.
Thank you, Paul. I'm just gonna make sure it's working. Okay, so I will start. So I will do a short introduction, an overview of this webinar. So I guess that some of you might not be aware of the FlexSNG project, so I will start with a small introduction. I'll talk about some of the advanced analytics that we have been using in the project. I'll turn to the Canadian team and do a short introduction of what we're going to present today, and I'll talk about the content of this webinar. So I'll start with a movie that was organized by FlexSNG, and it's a short 2 minutes movie, and I want you to listen to this.
In the first quarter of 2022, short-term gas prices were on average 5 times higher than 2021. Bio-based fuels reduced dependence on fossil fuels, offering new, economically viable solutions. FlexSNG is a showcase research project that can use a wide variety of low-quality biomass residues and biogenic waste as feedstocks to produce 3 different outputs, whilst developing and validating a flexible and cost-effective gasification-based process. Biomethane, a near-pure source of methane. Biochar, a charcoal-like substance used to displace fossil feedstocks in energy production, industry and in agriculture. Renewable heat, the byproduct heat is used for district heating or sold as renewable steam to industry. By making use of all 3 products, the process reaches over 80% overall efficiency. The process adapts to changes in market conditions, local feedstock availability, and price by easily switching operation mode, either co-producing biochar and biomethane, or maximizing only biomethane production. The concept aims to be 30% more cost-effective compared to state-of-the-art biomass-to-SNG designs. In addition to the social and environmental benefits brought by the project, FlexSNG also supports 4 of the UN Sustainable Development Goals. FlexSNG involves 12 partners across 8 countries running for 3 years until May 2024, with an overall budget of 4.4 million euros. The project is based on an international cooperation between Europe and Canada, bringing additional benefits such as knowledge transfer and wide geographical coverage. For more information about the project and partners, please visit our website www.
So there was a movie, just to sum it up a bit. So it's a international collaboration between the EU and Canada to strengthen the collaboration in the strategic sectors of bioenergy and biofuels. As you heard in the movie, it was supposed to finish in May 24. It's an extension, and it finished now in December, and the Canadian part will finish in March next year. There are 12 partners. They're both industrial partners, academic partners from 8 countries, which has an expertise in a number of different disciplines, and you will hear some of those expertise today. The FlexSNG is coordinated by VTT in Finland, and the Canadian team is Polytechnique Montréal, Université Laval, so we are an academic partner in this collaboration, and we are funded by a federal and a provincial funding organization. The goal of the FlexSNG is to develop and validate a flexible and cost-effective gasification-based process for the production of pipeline quality biomethane, high-value biochar, and renewable heat from a wide variety of low-quality biomass residues and biogenic waste feedstock. So that's our definition. And what we have, we really have one plant, but we can run in 2 different modes. We can have a co-production mode when we produce biomethane, biochar, and heat, and one where we focus more on the biomethane and also heat. In this case, the biochar is used to mix with the raw material. There are 9 different work packages in the FlexSNG, and in other webinars, they've been talking about other work packages. Today, we will focus mainly on the work package 2, which is optimization of the feedstock supply chain, and also on work package 8, which are the case study and some of the environmental analysis and business potential. And of course, work package 9, which is a part of this webinar for the dissemination and communication. The case studies, there are a number of case studies, and they are divided in 4 different regions. So today we're going to focus more on the Canadian one, but there are also the European, there's a North European, South European, and a Middle European one with a number of case studies. And each of those cases have different characteristics that are used to validate the process. In the project, we have set some very tough goals or challenges. So when we look at the optimization of feedstock, we would like to see a decrease of the cost of 20%. For the conversion process, the CAPEX, we want to see a reduction of 30%. And for the overall biomethane production cost, we are looking at a reduction of 30%. So these are our challenges that we put ourselves for in the project. Today's seminar, we'll talk about advanced analytics, and the definition is really the scientific process of transforming data into insights for the purpose of making better decisions. And this is a collection of different data techniques, and you will see optimization, machine learning, multi-criteria decision-making models. And all these are used to improve decision-making for the businesses. And in our case, we really look at analytics as a key for evaluating the large capacity biofuel processes. So when we have those processes, they're very close to profitability. So we are looking at seeing how we can reduce the cost or to make those profitable. And what we're going to see here is that data information comes from many different sources. So you can think about big data. We're going to see about some of the optimization models for transport and processes. These are important tools to meet those challenges I just mentioned. We look at value chain to look at all the aspects to coordinate the logistics activities in each of the chain. And also because we are looking at multiple resources, we're also looking at collaboration between value chains. So that's another type of challenge that we have to really coordinate these chains so we can use them where they are our best fit. So the Canadian team is really, like I said, we have 5 projects. There are 3 from Polytechnique Montréal, which are more on the chemical side. And we have 2 projects from Université Laval, which are more on the logistics side. So what we're going to do in the presentation here is to really look at the Canadian case study and look at on this as a high capacity biofuel production processes. And what we're going to look in this seminar, which you're going to look at the issues are, low biomass feedstock costs, even if we have large volumes from advanced harvesting processes, the feedstock flexibility and delivery optimization. We have the process technology is capital intensive, so reductions are critical, and small difference in yields or processes available can significantly change the cash flows and the process which is running. And also the manner that the process integrated with adjacent processing facilities via industrial symbiosis is critical. So in this seminar, we will hear a number of these projects. So I started with the introduction. Simone will talk about an overview of the FlexSNG study cases. Rozita will turn to talk about more technical planning, the integration of biomass value chains, the forestry, agriculture, and MSW. Asudeh will look at more operational route planning for the FlexSNG Biomass-to-Bioenergy Project. Yasaman will look at biomass pretreatment trains for the FlexSNG gasification process. Tunet will look at leveraging industrial symbiosis to improve FlexSNG process economics. And then Simone will come back and talk about techno-economic analysis of the FlexSNG process in the study cases. And to finish up, Paul Stewart will run the wrap-up discussions. So with that, I'll give the word to Simone, please.
Thank you very much, Mikael. I'll now share my screen. Okay, so I'll start now by talking about the Canadian case study, the context and design basis. So I'll go over the overall project context and methodology. I'll present our industrial partner, Greenfield Global, and I'll talk about design basis and case studies. I'll finish with the key questions this webinar will answer. So as presented by Mikael, we have 4 main case studies in the FlexSNG project, 3 in Europe and 1 in Canada. All these case studies integrate feedstock prices and availabilities from their local context, biochar and gas market prices, industrial integration possibilities, and policies and legislation from their context. In these case studies, we have 2 main goals, as said by Michael. The first one, to target a 20% reduction in feedstock supply cost by developing and optimizing cost-effective feedstock supply chains. And the second one, to provide preliminary cost estimates of industrial scale FlexSNG plants while targeting 30% reduction in capital costs through a number of improvements and technology innovations. Our Canadian case will look at 9 case study variants. So how did we get to the case studies? First of all, there was some experimental work done on the gasification pilot plant by VTT, a research center in Finland. This allowed to close some mass and energy balances that were afterwards modelized to generate some simulation for the case studies. With these results, capital and operating cost estimates were gathered from industrial partners, which led to technico-economic analysis of the case studies. In this Canadian case study, Université Laval is looking at feedstock logistics and costs, and Polytechnique Montréal is looking at pretreatment, industrial symbiosis, and TTA, technico-economic analysis. So now, our Canadian partner, industrial partner is Greenfield Global. They are based in Varennes, Quebec, and they are operating since 2007. For those who are familiar a bit with Quebec, it is near Montreal. You can see here behind Greenfield Global, the St. Lawrence River. Greenfield Global, they produce the lowest carbon ethanol in Canada, up to 190 million liters per year. And they have some big expansion plans for the Zero Fossil Horizon 2030. They are having a 60 megawatt electrolyzer installed next fall. This is for their methanol production projects. They're also having an expansion for their ethanol distillery. And this is a great context for some case studies because there is going to be some available oxygen from their installed electrolyzer. They're also seeking to invest in some new bioenergy products, and this ties greatly with our case study goal, which is to explore the potential for FlexSNG, contrasting with other gasification technologies and their implementation on the Greenfield Global site. So our design basis for our case studies is designed on 3 types of feedstock that are available locally: forest residues, agricultural waste, which is wheat straw in our case, and municipal solid waste. Feedstock residues is a competitive feedstock here in Quebec. Sawmills are closing, so they're available at large capacities. Wheat straw is interesting because there are some existing value chains and brokers, and they're available at close range as Greenfield Global is near some agricultural zonage. Municipal solid waste is also available closely. We are near some big urban centers. However, there is a complexity of triage for this feedstock to get to solid derived fuel, which is to be put in the gas fire. And there is also a risk with this feedstock because there is a neighboring plant in construction that is seeking to use this feedstock. We will look at capacities ranging from 500 bone dry tons a day up to 3,000 bone dry tons a day in our case studies. In megawatts, this is from 100 to 600 megawatts from the feedstock basis. So for our case studies, we took the 2 plant, 2 modes configurations. The first mode, as explained by Mikhail, produces biomethane, biochar, and heat. And the second mode maximizes production of biomethane. And the second mode is the one that's more applicable to our cases because of the competitiveness of the price of biomethane relatively to biochar in our context. The plant, FlexSNG plant, is also tailored for conditions regarding feedstock and location. In our cases, the best configuration in most of the cases, the biorefinery, 1 single line of gasification. However, we will also look at 1 case where there is the city refinery configuration, so dual gasification lines for more challenging waste feedstocks. Here are our 9 case studies from the Canadian context. You can see that we have 5 forest residue cases ranging from 500 bone dry tons a day up to 3,000 bone dry tons a day. We have these 2 cases that are on the same feedstock basis. However, there is an impact regarding a possible innovation regarding temperature that is looked at in the second case. There is a wheat straw case also to solely look at this low cost agricultural feedstock. And we have 3 mixed feedstock cases that look in mixing more challenging feedstocks with wood. We also have here our city refinery case. So what are the key questions that will be answered in this webinar? First, how can collaboration across forestry, agricultural, and MSW value chains improve biomass to bioenergy logistics and lower feedstock costs? After, we will look at what are the benefits and challenges of optimizing feedstock logistics through truck steering strategies in daily operation and road planning. We will also see what are the estimated cost and technical considerations for various pretreatment trains, including the potential for heat integration in the gasification process. We will look at what are the practical solutions that can enhance economic and operational benefits of the FlexSNG process through industrial symbiosis and strategic collaborations. And we will finish by answering what are the key results of the technico-economic analysis of the implementation of FlexSNG case studies in the Canadian context. So thank you very much. I will now leave my dear colleague Rozita talk to you about her work.
Thank you so much, Simone. So hello, everyone. So I'm going to share my slides here. I'm Rozita Ebrahimi, a PhD student at Laval University. Today, I'm going to talk about the tactical logistic optimization for the FlexSNG Biomass-to-Bioenergy Project. Here you can see the presentation outline, and I'm going to talk about these contents in order. So let's start with the first line, which is the context of this work relative to the FlexSNG process. You already got familiar with the FlexSNG. It's a new gasification-methanation process to produce biomethane and biochar with the aim of 30% reduction in the conversion cost. But this work, which is the procurement part of the FlexSNG, has the aim of 20% reduction in the feedstock supply cost. Actually, this work is going to provide the raw material for the gasification process, which is the biomass. And this biomass comes from different value chains, different sources, like the forestry value chain, agricultural value chain, or municipal solid waste, MSW value chain. The overall objective here is making a collaboration between 3 different biomass value chains by exploring the differences and similarities of the logistic operations between them. Actually, we know that there are factors, some uncertainties that affect the logistic operations, affect the value chains like seasonality, time of harvesting, quality and quantity of the biomass. So by knowing them, we are going to have a tactical or annual planning. So when we talk about the logistic operations, I would rather to talk about the locations first. The beginning places or the supply zones in the forestry biomass value chain are the harvesting areas where we cut the trees and we pick up fuel logs and residues there as the biomass. In the agricultural biomass value chain, we consider farms as the beginning point and we pick up wheat straw, for example, as the biomass there. In the MSW, we have eco centers as the beginning points. There are different categories for the municipal solid waste, and we pick up only the woody MSW for this project. So the first logistic operation here is harvesting and collection. After that, we have intermediate facility locations or terminals, and at the end of the line, we have biorefinery yards. So we can do some logistic operations there because of the limited space that we have there. Chipping is the other logistic operation. It is really important because we need to have a smaller size of the biomass to tackle the bulkiness. It helps us to reduce the transportation cost. And after that, we can mention drying. Drying is important because we need to control the moisture content of the biomass because it is important for the gasification process. We can do the chipping and drying in different places with different machines and with different costs. We can mention transportation. You know that transportation is the most important logistic operation with the highest share of total cost. We can consider trucks, trains, or other transportation modes. Storage is also important. In the tactical planning, we need to have a continuous flows of the material during a year. So we need to cover the possible shortage of one period with the volume of the other period. So storage helps us to tackle those uncertainties. And finally, we have conversion. So if I want to talk about the gathering data for the Canadian case study for this work, it's a biorefinery placed in the Varennes area. I use different websites like Forêt Ouvert website for forestry biomass value chain, Biomat website for the agricultural biomass value chain, and Reci Quebec website for municipal solid waste value chain. They are governmental website. They provided some geographical information. I extract the required information from them by some tools like GIS tools, Python, and I create a larger scale database for this project. So to talk about the collaboration mechanism, I would like to provide an example for you. Here you can see the assumption of this example. There are 3 sources of the biomass. There is actually a transportation mode, 2 transportation modes here. The first one, truck system. The second one, train and truck together. Considering terminals is an option, we are going to know how having terminals affect the optimization results. And finally, for the demand, I consider only one production plan because there are different production plans for the FlexSNG, and I pick up only one of them as the demand of this example. And there are some logistic options in this example. Option 1, we don't have terminals in the system and shipping occurs at the roadside and at the biorefinery. Option 2, again, we don't have terminals in the system, but shipping occurs only at the roadside. In option 3, we consider some terminals in the system and shipping is allowed in every possible places like roadside, biorefinery, and terminals. And in option 4, again, we have some terminals and shipping is allowed at the roadside and terminals, but not at the biorefinery. So, to solve and analyze the optimization system, I use Woodflow. Woodflow software is a powerful tool from one of the FlexSNG partner, a creative optimization company, a Swedish company. So I use Woodflow to do the optimization. And let's go through the collaboration mechanism as an example. Just imagine that we have only forestry in the system. It is the base case. What does that mean? It means that the 100% of the demand can be satisfied by the forestry. In this table, you can see the total annual cost for different logistic options for 2 transportation modes. One of them is the truck system, and the second one is truck and train system. So when we add a train to the truck, you can see that we have some saving in the total annual cost. It means that train is the cheaper transportation mode and help us to get biomass from the farther area, not only around the biorefinery. So it helps us to have those saving in the transportation cost, which affect the total annual cost. But what happens if we have another player in the game? We add agriculture to the forestry, and at the first stage, we just assume that there is no collaboration between them. We split the demand of the biorefinery into 2 percentages, 80% for the forestry and 20% for the agriculture, and they work separately. They just focus on their own demand to be satisfied. So you can see the results of the non-integrated system when we have only truck in the table. But what happens if we have a collaboration between them? You can see the new results here. When we have a collaboration between them, they don't have a predefined demand at the first. They collaborate with each other. For example, in the fall season, in the rainy weather, when we have a less access to the forestry area, we can use the agricultural biomass value chain because the harvesting time in Canada for the agriculture value chain would be in the fall season. So we have access to that kind of biomass and we can cover the shortage of forestry with the agriculture. And here you can see the different demand satisfaction sharing. After optimization, we find out that 68% of the demand is satisfied by the forestry, 32% by the agriculture, and you can see the more involvement of the agriculture in the collaboration system. And we get also the saving from this collaboration. Here you can see the saving. But what happened if we add the train system by that logic that I told you? Adding train gives us additive saving and we can save more when we have train and collaboration together. So let's add another player to the game, MSW. First, we assume that there is no collaboration between them and we have a non-integrated system. 80% of the demand should be satisfied by the forestry, 15% by the agriculture, and 5% by the municipal solid waste. So you can see the results here. But when we have a collaboration, after optimization, we find out that 51% of the demand was satisfied by the forestry, 27% by the agriculture, and 22% by the municipal solid waste. And here we can see the more involvement of the agriculture and MSW in the demand satisfaction, and we get the saving from this collaboration. You can see here, we have at least 21% saving for all logistic options that we have. And when we add train to the system, we can save even more. Here, the best saving that we have is for option 4, 24% saving. So I just provide 2 maps for you. The first one, the left side, is the truck system when we have the activity, the transportation movement around the biorefinery. The red spot in the middle is the biorefinery location. And here you can see that by the truck system, the model preferred to have a movement around the biorefinery to reduce the transportation cost. But in the right side, you can see we add train to the system. Train help us to get the biomass from the farther area. You can see that we have some activities in the farther area around Lac Saint-Jean, and the train bring the biomass to the biorefinery, and we can have saving from these transportation mode. So if I want to have a brief conclusion, we know that having collaboration between different biomass value chain get us at least 20% saving, and having intermediate facility locations, terminals, and chipping at the roadside and terminals, which was the option 4, if you remember that, give us the best saving, which was the 24% saving. And in option 2 and option 4, when chipping is done at the roadside, it means the beginning points of the logistic. And at the terminal, in the middle point, we achieve better saving in the collaboration in 2 transportation modes. So my presentation done. So let's go for Asudeh and see her presentation. Thank you.
Thank you very much, Rozita. You will see my presentation in a few seconds. Here you are. Today I'm here to share some insights on operational route planning for the Biomass-to-Bioenergy project. This work is to support the FlexSNG gasification-methanation process using advanced analytics and optimized solutions for the feedstock supply at the operational level. First, I will introduce the goals of FlexSNG that we are going to support. Then I will present the methodology and the advanced analytics that we used. Then there is a representative case study and the results, followed by the concluding remarks. This specific work is to support the first goal of FlexSNG, which is to reduce the feedstock supply cost by 20%. And as mentioned earlier by our colleagues, the biorefinery in Canada is assumed that is supplied by 3 sources of feedstock, like agriculture waste, municipal-side waste, forest residue, and also some byproducts from forest industry. Our idea is to integrate the 3 sectors to have a better planning at the operational level for the transportation of not only biomass in the 3 sectors, but also other products which are transported in the 3 sectors, like transportation of round wood to forest industry, other type of waste to recycling plant, and also food crops to food industry. I said that I am focusing on the operational level. Actually, transportation plannings are made in 3 levels of decision making. The highest level is strategic levels, which take a long horizon for several years. But if we take midterm horizon, the decisions are at tactical level, what Rozita explained. But me, in this work, I'm specifically focusing on at the tactical level, the planning periods are monthly or weekly. And me, I'm focusing on operational level, where I take shorter horizon, like a week or a month, and periods that I take in the planning is can be daily or even shorter plans. And at this level, the decisions are for the routing, the individual routing for each available truck. And if we assume this as an example in the 3 sectors, in the non-collaborative scenario, when the 3 sectors are not integrated, this can be an example of their planning at the operational level. You can see they have their own fleet of trucks, their own planning. Each of them have their own orders to satisfy. But our idea is to integrate them and consider the whole problem as one integrated routing problem, where we propose one integrated routing for all the trucks which are available in the 3 sectors. If we integrate them, this can be the example where the trucks are shared on the nodes are highlighted by red line. And this type of truck sharing means that we see wherever possible, we share the trucks among the 3 sectors. For example, if in one sector there is one truck with a configuration which is compatible with the assortments in another sector, we share the truck with other sector. And this kind of truck sharing has both benefits and challenges. The benefits are twofold. First, reduction in the transportation time and the transportation distance. And the second one is the number of total trucks that we need for the transportation in the whole planning. But also there are some challenges. The challenge here is when we share the trucks, sometimes additional operations are needed, which add new cost to the system. It means that, for example, if we truck wood chips truck from agriculture sector with the from forest sector with the agriculture sector to transport food crops, we need to clean that truck, and this type of operations add additional time and cost to the system. So to support our idea of truck sharing at the operational level transportation planning, we use optimization techniques. The tool that we provided has 3 main steps. The first step is to solve 2 optimization models. We solve 2 optimization models because there are 2 links in the network and these models are to determine the important links in the network. Transportation of biomass, you may know that, are in full truckloads, and every time a truck transports a full truckload, it needs to take another trip empty to reach another supply node. So there are both loaded trips and unloaded trips. To determine those links in the network, we solve these 2 optimization models. And once the network is ready, we use another tool to generate detailed routes for all the possible truck types that we have in the network. Then finally, another optimization model is used to select the optimal route for each individual truck. This tool is implemented on Python, and we used QGIS and also Excel for the purpose of visualization and data storage. The tool is now ready to be implemented on cases. Here we propose a representative case study in Canada. You see the biorefinery named GFG in the middle, right outside of Montreal. And we assume that there are some nodes around this location in the 3 sectors of agriculture, forest, and MSW, or municipality solid waste. And the total volume to be transported in this example is 4,500 tons, which is both in the biomass transportation, about 1,500 of it is biomass transportation, and the rest of it is for the transportation of other products that we have in the 3 sectors. The reason we consider other products is for the truck sharing, we can find more opportunities for truck sharing. The larger the area, the more opportunities for truck sharing, and consequently more reduction in transportation costs. And also we assume we have 4 types of trucks: one for round-wood transportation, one for chips transportation, another one for solid waste transportation, and also one agricultural truck. You can see that the first truck has different configuration, but the rest of the trucks have similar configurations, and they can be shared with the other sectors. In order to plan this network, in the non-collaborative scenario where the trucks are not shared, we have about 130 full truckloads to be planned in 1 day planning. And we solve this example by the proposed tool. You see the comparison between the collaborative and non-collaborative scenario. As I said, the first truck has different configuration and it is not shared with other sectors, but the 3 other trucks, you can see that some of them are used more than the case in a non-collaborative scenario. For example, the chips truck has better capacity and it is used more than before. And what is important here is the number of trucks that is reduced totally, and it is by 8 truck in this example. We made another comparison in terms of the working hours of the trucks. The trend is the same, obviously, but the reduction in the transportation time used by all the trucks is reduced by 9%. This is a reduction that we gain from truck sharing in the 3 sectors, but this is beside the saving that we gain from optimization itself. And in summary, we propose a methodology based on truck sharing strategy to integrate the 3 value chains for a more efficient planning. As I said, we consider larger area, larger of number of products in the 3 sectors to find better opportunities for collaboration and truck sharing, and finally, more reduction in transportation costs. Then we used, as I explained, 3-step approach, which use optimization tools. Optimization tools is very powerful, has proven to be very powerful in transportation planning. And the methodology that we proposed has 2 main benefits. The first benefit is about the methodology. For the vehicle routing problems, in the literature, there are many approaches. But if we count only on the classical methods in the literature, we cannot solve even a small problem because this type of problem is very complicated, and there is a need for creativity to make it appropriate for every specific problem which is implemented on it. And from that point of view, our methodology is quite efficient to solve a large case of FlexSNG. And the advantages that we gain from the collaboration, comparing it with the non-collaborative counterpart, is a 9% reduction in the transportation time. And as I said, this is beside the saving that we gain from optimization techniques. Totally, what we contribute to the 20% reduction, which is the first goal of FlexSNG, is even more than 20%, which FlexSNG asked. This is the 9% reduction that I make in the from operational point of view, beside the 20% reduction that Rozita gained at the tactical level planning. Thank you for your attention. Now I leave the screen for our colleague, Yasaman from the Polytechnic Montreal.
Thank you very much, Asudeh. Hi everyone, my name is Yasaman Kazemi, and today I will present biomass pretreatment trains for the flexible gasification process. I will begin my presentation with the context of my work relative to the FlexSNG process, and next I'll talk about the overall project methodology and move to the heart of my presentation, which is identifying low risk or minimum risk biomass pretreatment trains for each of the feedstock, which led to the discussion on pretreatment train cost estimate for the Canadian case studies, and finally conclusion. As you know, FlexSNG process is a biomass-based process, gasification-based process for the flexible production of biomethane and biochar heat from agricultural biomass, forest residue, and municipal solid waste. And the key goal of FlexSNG is to reduce the biomass supply chain by 20%, which is related to my work, because pretreatment is a critical component of biomass supply chain, and it can reduce the supply chain cost by optimizing pretreatment train and finding suitable pretreatment trains. We also can impact the downstream processes. So the objective of my project is to develop a systematic framework to identify the candidate pretreatment train for the FlexSNG gasification process. For different pretreatment are devised for different feedstocks. So basically, different pretreatment trains are required if you are using different feedstock. In order to find the candidate pretreatment trains, I will start by looking at minimum risk pretreatment trains, which are operational at the industrial scale and have low risk, but are usually expensive. And then I look at alternative pretreatment options defined by considering variance on the technology units like different drawings, or variance on the overall pretreatment train, like using torrefaction or pyrolysis, which again increase the risk but have potential for return. And finally, I will look at the possible pretreatment trains which can handle mixture of feedstocks, and it again increase the risk but has potential cost saving. So the trade-off between the different pretreatment trains will be evaluated. The trade-off between risk and return will be evaluated to find the candidate pretreatment train. However, today the focus is on minimum risk pretreatment train for the target feedstock. In order to find the minimum risk pretreatment trains, we first conducted a global survey for commercial scale biomass pretreatment plants, either at gasification or pyrolysis plant, to understand what are the existing pretreatment solutions for the target feedstock. And then we triage the number of options to ensure that they meet the feedstock specification by the gasification, by the FlexSNG gasification. And then we devised minimum risk pretreatment trains for the target feedstock. And we considered heat integration in our design. And then we obtained the capital cost codes from the most leading suppliers of the pretreatment technologies, and approximated the capital cost for the Canadian case studies. As you know, that's what we have found from our survey. For FlexSNG, usually a mobile chipper is used, followed by a belt dryer. And there are some examples of gasification power plants like Technip and Jutseno, which use belt dryers, but rotary dryers are also used, like in Gaussing biomass gasification plant. And this is the same for with straw, but instead of mobile chipper, a two-step shredder is used. But for municipal solid waste, it's much more complex, as it has to convert to solid recovered fuel, or SRF. After initial shredding of municipal waste, ferrous and non-ferrous metal are usually separated from the waste using magnetic separator and eddy current or manual separation. And fine screen is also used to screen out the non-combustible, and then followed by a wind swifter, which removes the heavy metal, and a fine shredder and a dryer. There are some examples of gasification power plant which use belt dryer, like Vyoma gasification and Inercam, but rotary dryers and fluidized bed dryers are also used at industrial scale. So considering the minimum pretreatment trains for the Canadian case studies, we assess the cost of pretreatment trains for each of the cases. And first, let's compare different pretreatment train costs for with a straw and FlexSNG at the same capacity. As you can see, at the same capacity, which is 500 dry ton per day, with a straw and FlexSNG, there is a slightly difference in between the pretreatment train cost, and for with a straw is slightly larger because it uses a two-step shredding. But for SRF, we can find that at the same scale, the cost is considerably higher than for FlexSNG and with a straw, and this is due to the complexity of the process and the additional steps involved, like a screening and separation and sorting. And for scaling up, we can see that the pretreatment train costs increase significantly by increasing the scale. but it's not proportional. So there's a little bit of economic of a scale here for at these capacities. So we highlighted the economic benefits of using multiple feedstocks and focused on the importance of recognizing the increased risk associated with this flexibility. And we figured out that optimized pretreatment trains can not only reduce the biomass supply chain, but also improve the downstream processes. And innovative pretreatment methods like mixed feedstock pretreatment can offer cost saving, but come with increased risk. Therefore, it's essential to evaluate the trade-off between the economic benefits that they offer and the added risk and complexity that they bring. And we also identified the minimum risk pretreatment strategies and cost-effective solutions for the target feedstock of FlexSNG gasification and their cost, and found that the feedstock type and, more importantly, throughput are critical factors influencing pretreatment cost. Thank you very much. I will now hand the presentation over to my colleague.
Good day, everyone. Today I'll be presenting on leveraging industrial symbiosis to improve FlexSNG process economics. So today we'll have a brief look at industrial symbiosis and the challenges faced when dealing with biorefineries. Next, we will discuss how a systematic design framework can be developed to address these challenges. And we will look at the Greenfield Global case study, as well as introduce the tool called Carbon Hydrogen Oxygen Symbiosis Network, which can be incorporated into the framework assessment, and then finally draw some conclusions. So the concept of industrial symbiosis delves from the classical definition as proposed by Shurto that where the focus is on traditionally separate industries that can improve their competitive advantage by having a physical exchange of material, energy, water, and byproducts. This exchange takes advantage of the collaboration and synergies made possible due to the geographical proximities of these industries. One of the most classical examples in literature of this is that of Kalundborg, located in Denmark. So, in the context of this FlexSNG project, where we have these specific goals which we are looking to attain, the question is then, is it possible that a potential for industrial symbiosis exists with the current waste streams and possible co-production available to FlexSNG? But it is not clear which combinations of symbiosis could bring the process to economic viability. So with this, we are looking, are these goals attainable and sufficient for the process to be economically viable? Can incorporating industrial symbiosis improve the process? And how much value will industrial symbiosis add? Next, let's look at how has industrial symbiosis evolved over the years and how this evolution has now incorporated network thinking, circular economy integration, broader scope of resources. So we're not just looking at physical materials, we're also looking at data exchange. The focus has been more towards sustainability goals and incorporation of those sustainability goals. And finally, also new technology integrations has made it possible for us to improve optimization and real-time tracking of resources. But there are various challenges that we face with regards to introducing industrial symbiosis into the mix of things. And these are things such as the technical, economic, regulatory and policy, organizational, as well as market and environment and social barriers. So let's say we have the policies in place that favor biofuel production. We have various sources of cheap biomass. and we can achieve the necessary economies of scale required to produce biofuels at a competitive price. We have a large-scale biorefinery that incorporates FlexSNG, but why is this still not sufficient for us to compete with commercial scale fuels? Can we bridge this gap by incorporating industrial symbiosis into the network? How do we quantitatively assess the impact of industrial symbiosis? To tackle the complexity of large-scale biofuel production, a systematic design framework is essential. This framework enables coordinated management of resources, waste streams, and partnerships addressing practical challenges such as fluctuating biomass availability, high energy demands, and the needs for economic feasibility. Biofuel refineries also produce multiple product streams such as biofuels, biochemicals, and bioenergy. The design framework incorporates these streams with other industry processes to maximize value creation while aligning operations with market demand and environmental goals. Central to the framework is the value chain, which ensures efficiency by identifying synergies at every stage from raw material supply to production distribution. And by focusing on the value chain, we can reduce waste, improve sustainability, and enhance the economic viability of biofuel production. Ultimately, the design framework lays the foundation for incorporating industrial symbiosis. With this framework in place, we can identify and leverage synergies between industries, ensuring that biofuel refineries operate not just as standalone facilities, but as integrated players in a broader, more sustainable industrial ecosystem. But how do we do this? And where do we do this in the framework? So let's look at how this design framework will be developed. So first off, we can look at defining the scope and resources, where the outlines are available inputs such as the biomass types and the carbon dioxide and energy. We will then identify stakeholders and key partners within the network, configure Symbiosis network by mapping out the potential synergies using the tool chosen, evaluate scenarios and simulate outcomes for each configuration, and then optimize and validate by refining and validating the framework and applying this to other case studies. And this is where advanced analytics would come into play. So let's look at the Greenfield case study. Currently, there is a symbiotic exchange of materials between Greenfield Global, as well as Cemex and Air Liquide, whereby CO2 and biogas are currently exchanged between these various industries. So moving on to the 2026 configuration, this is where a phase 2 electrolyzer will be implemented at Greenfield Global. And an additional synergy which could take place then is where oxygen is then provided to Air Liquide. Moving on to 2030's configuration, we can then have where FlexSNG could potentially be incorporated along with the electrolyzer and Greenfield Global, and we could have additional synergies such as heat and energy exchange take place, as well as a circular economy of carbon dioxide, methane, and biomass valorization with various industries. So next, if we look at what are the additional scenarios that can take place in 2030 plus, we have where we can look at potential partners such as Enerchem, Kronos, as well as Chimera for additional exchange of materials. So how are we going to evaluate this? By looking at carbon, hydrogen, oxygen symbiosis network, which is like a matchmaking tool. It helps companies figure out how to share resources more efficiently by analyzing how carbon, hydrogen, and oxygen, which are the building blocks of many materials and energy systems, move through different processes in order to produce final products. So here we have our feedstock, which gets broken down into the components of carbon, hydrogen, and oxygen. We have an available network of different industries that can process these components. And then finally, we can look at what are the products that we can produce, such as bioSNG, biochar, energy or heat, as well as other products. So the general design methodology and formulation for Chosen looks at evaluating the available inputs at an atomic level. It identifies the different products that can be produced within the available network, and then further on, evaluate the various network configurations and optimize these for specific objectives, such as maximum feed profitability. So with this, when we're looking at the different sort of steps in this, and how the desired objectives and potential networks can vary. If we look, for instance, a similar network with different, with the same configuration, it might differ if we're maximizing for profit versus if we're minimizing for waste. Lastly, the challenges to determine, so when we're looking at the challenges to determine whether integrating industrial symbiosis and technologies like FlexSNG at Greenfield, how can we overcome these with the barriers faced when producing large-scale biorefineries? Chosen can be employed to track the flow of resources like carbon dioxide and biochar between industries, identifying the optimal exchange that maximizes value and minimizes waste. Chosen can also be tailored to model large-scale operations, including high biomass throughput and multiple outputs, such as biochar and bioSNG, which are unique to the FlexSNG process. Integrating industrial symbiosis into FlexSNG operations at Greenfield Global could lower CapEx by 30% while increasing profitability by leveraging synergies like heat sharing and biochar monetization. And further, by adopting these strategies, Greenfield Global can position itself as a leader in sustainable biofuel production and industrial innovations. So, thank you very much. And next up is my colleague Simone, who will talk to you about the techno-economic analysis of the Canadian case study.
Thank you very much, Tunet, for your presentation. I will now, for this last presentation of the webinar, focus on technico-economic analysis of the FlexSNG process in the Canadian case study. So I'll go over technico-economics, how our model was structured, how we benchmark our capital costs against other gasification technologies, and we'll finish by an analysis of results and a conclusion. So why is TA so important in our work? It's because it evaluates the economic viability and profitability of the projects. So it identifies the critical economic factors that assess the project viability. We know that bioenergy projects are capital intensive. Similar projects in the past have failed due to underestimated costs. This highlights the need for systematic cost estimation and analysis, especially in technology projects that look at technology that's in development. TA supports informed decision making. It provides a framework for understanding economic viability before scaling up, and it highlights some key performance metrics such as net present value or internal rate of return. So classical techno-economic approach is to get capital cost estimates and operating cost estimates, which tie into some economic performance metrics such as return on investment. These can be further analyzed with sensitivity analysis, which brings an insight into risk, or scenario analysis, which bring an insight into robustness. So how did we gather our capital cost estimates for the FlexSNG Canadian case studies? We gathered our equipment costs from the 4 big process sections that we determined: gasification, methanation, pre and post processing, which includes the pretreatment trains that were talked about from with Yasaman's presentation, and post processing with the final gas compressor. Balance of plant is the wastewater treatment, heat integration of all the process, security items, etc. So for all these 4 big process sections, we gathered direct and indirect costs, which brought us our capital expenditures. We also looked into some government support to help de-risk the technology, which would apply to the capital expenditure. For our base economic case, which is the forest residue 500 case, we obtained a capital cost estimate of $540 million Canadian. But how does this compare to other projects? To benchmark our capital costs, we looked into projects where the capital costs were available as well as the capacities, and projects that had similar processes as the FlexSNG process. So first of all, the Gobi Gas project. It's a well-known, first-of-a-kind gasification project that was done in Sweden, and it used a gasification technology to convert woody biomass into biomethane. It had over 1,000 hours of continuous operation when it closed, and so it has a pretty high technology readiness level. The major differences with FlexSNG is that this project used a dual fluidized bed gasifier, which is different from the gasifier used in FlexSNG, and was demonstrated on a smaller scale than Flex. When we actualize the cost from the Gobi Gas project to our targeted capacity for an economic base case and actualize them, we get $795 million Canadian. We also looked at a second gasification project, which is the Enerchem RCV project, which is a plant that is building right next to our industrial partner, Greenfield Global. They are seeking to gasify MSW, municipal solid waste, to generate bioethanol. Their main difference with FlexSNG is their target, which is the main feedstock to be MSW, and also the cost that we got also considers the electrolyzer. So we get, when adapted to our case, we get a $993 million Canadian benchmark. So for comparison purposes with our case, we chose to compare mainly to the Gobi Gas project because of the same end-of-the-line product and the most similarities. So when comparing these two costs, we get a 32% capital cost reduction. We went to look further into the cost of Gobi Gas to compare them to FlexSNG, and we detailed the process sections where the costs were associated. However, we can see that it is not clearly linear because of the way that we done our estimates. Gobi Gas regrouped all the other project costs in one big category seen at the end of the column, as we use the other project costs and disperse them in the two other columns. So we decided to focus more on the differences that would really justify this cost reduction. First of all, Gobi Gas has a significantly smaller scale. It was developed at 20 megawatts. We're seeking more in the 100 megawatts in this base case. This means less opportunities for synergies in the process or less scale-up optimizations. Also, there are two different gasifiers that are used. Gobi Gas uses a dual gasifier versus a CFB in Flex. The gasifier in Flex can be scaled up to 200 megawatts, which is significantly higher and higher efficiency. There is also different backend technologies in both of the projects. However, FlexSNG incorporates some innovations and simplified process steps, which all justify this capital cost reduction from Gobi Gas. So now that our capital costs were benchmarked, let's move on to the operation costs. So the main assumptions here, looking at the feedstock costs that were provided from Université Laval, you can see the dollars per ton that were assumed. The agriculture waste and MSW are less expensive per ton than the forestry residues, and forestry residues, the cost goes up as the capacity and distance goes up. We also have some cheap power costs here in Quebec. We are lucky to have some available hydroelectricity. So these were the main assumptions used for the OPEX. For our main revenue streams, we have 4 streams. So starting with the biochar stream, market price of $150 per ton was assumed because of the high fixed carbon biochar that is generated from the gasification process. This is assumed a price to be dispatched by char brokers. Also, our main revenue stream, bioSNG, has a $30 to $35 per gigajoule value here in Quebec. This is from contracts that are currently being negotiated with Énergir, the main gas provider in Quebec, which has targets to get more renewables in their pipeline. So this is why the cost is so much higher than non-renewable SNG. Well, non-renewable natural gas. So afterwards, we have 125 PSC saturated steam stream, which is generated from the low-grade energy that is issued from the FlexSNG process. This would be integrated in Greenfield Global's distillery. However, we do have an inconvenience in Quebec, is that we have no other outlet for the low-grade process heat. We do not have district heating. We have one last revenue stream, which is the CO2 stream. This stream is of high purity CO2. However, we do not have current possible varialization with the neighboring plants. So moving on to the main economic results, you can see here all the case listed from the smaller capacity cases, D1, D2, to the higher capacity cases. I will now show you the net present value we get with a WACC assumed of 8% and IRRs. As you can see, we generate a negative net present values. However, we do have some interesting IRRs that start to get in the higher capacity cases. As you can see, if we put next to next the OPEX revenues and total capital installed cost, we generate higher revenues than OPEX with a small margin. The revenues is mostly due to the SNG revenue, and the small margin compared to the high total capital installed cost shows that we generate smaller revenues. So finally, a quick critical analysis of these results. The cases with high capacities perform the best. They do have a high capital cost, but their high revenue due to mainly SNG makes them perform better. The cases with mixed feedstock did give a reduction in feedstock costs with a cheaper feedstock than forest residues, the agriculture waste and the MSW. The better performance was associated with municipal solid waste relatively to agriculture waste. And however, there is a higher risk of operation with these waste feedstock, especially in the city refinery case, where there is a gasifier operating solely on MSW. Canadian cases are unfortunately disadvantaged from the European cases because there is no access to district heating revenues. So in conclusion, TA was performed to answer the big goal, can capital costs be reduced by 30%? Our methodology included gathering capital costs for the process sections and compiling operational costs and revenues from mass and energy balances, and the scaling factors that were used were adapted for large capacity biofuel processes. So this is officially the end of the webinar presentations. I hope you were inspired by these the nice 5 research presentations that we heard. The goals for our project were to reduce by 20% feedstock supply costs. This was achieved through optimizing feedstock logistics, and to reduce by 30% capital cost. This was achieved by considering preliminary technico-economic analysis with insights on pretreatment costs and industrial symbiosis. Thank you very much for all your attention. Now I'll leave Paul for the questions and answer session.
Thank you very much, Simone. I'm going to self-congratulate here. A great series of presentations, really covering the gamut of advanced analytics we might use to analyze and seek winning conditions for this big challenge of economic viability for a large capacity biofuel biorefinery. While everybody's putting their questions, I'll go to live questions in a little while. I thought we might go back to two of the questions that have been asked and responded to, but just to elaborate a little bit. One of them is by Michael Borg, and he's asking, it's kind of an open-ended question, and so Rozita and Mikhail have done a good job trying to answer it with words, but I thought you might want to elaborate on the sorts of assumptions pertinent to Michael's question.
But I need to check which one I answered on.
Yeah, he kept coming back to the assumptions that are behind, in particular, Rozita's costs, who then said, well, maybe it's also an operational.
Yeah, so I mean, the assumptions are, because in the technical project, we have many supply points, whether they're agricultural sites or forest sites. And what we do is we don't make any assumption on average distance, because we actually use the real distances that trucks are actually transported. And the costs are based on typical agreed, well, there are agreements between different suppliers and demand points, but typically we use average cost for those transports. And again, there are not really any assumptions on average cost, but they are sort of computed within the model because they are specific between supply and biorefinery points.
Are you happy with that, Michael? I'll take that as yes. The other question I thought I'd come back to is by one of our best question askers, Hamid Bashiri, and he asked at one point, may I know which gas cleaning technology is being used in FlexSNG? And of course, that's the secret sauce in many ways for carbon efficiency and gas cleanup, and really critical to being able to use mixed feedstocks. So I thought Simone or maybe Mina, who's also here, might want to add to the discussion a little bit. There's been a short answer put there, but maybe there's a comment or two added.
Yes, well, I can answer a small answer, but I know Mina is the expert in place. I don't know, Mina, are you able to open your microphone? Well, while she's figuring it out, I can start an answer. Well, oh, there she is. Okay. Well, so the FlexSNG has a hot gas cleaning of the raw gasification gas that includes a hot gas filter and a catalytic reforming of tars. And afterwards, there is some innovative sulfur removal process, which is on a dry basis. And there is also the catalytic methanation, the Vesta catalytic methanation. So I don't know if you wanted to add on that, Mina, with all your expertise.
Oh, hello. Can you hear me?
We hear you, Mina.
Yes.
Yes.
Oh, it was just like Simone added. I write a comment in the catalytic reforming and hot filtration. That is our system there. So thanks.
Thanks, Mina. And maybe just to complete that picture, Sumitomo is involved in FlexSNG on the gasification side, and would, to segue into the next question about methanation technologies and catalysts, and Wood is involved on the methanation side in respecting the confidentiality of their equipment, and so that division of scope in the gas cleanup was done correspondingly. Hope that answers your question. And Leon, do you have anything further you would like to ask other than understanding that it's Vesta methanation by Wood? Super. There's Leon. Yeah, I think you're unmuted now, Leon. Okay, so now we go to, I guess, live questions. If anyone would like to ask anything in the last few minutes that we have here, if you have a burning question, please feel free to open the mic and ask some questions.
Well, I see a question in the chat from Cedric Tifo.
Good.
I can maybe state it so everyone knows. So he asks, what high prices for SNG in Quebec will certainly not last for decades. However, economics do not seem to be promising. What are, in your opinion, conditions to make the FlexSNG process attractive? So I can maybe start with an answer that I would see. Well, we looked at some great examples with industrial symbiosis. I feel that could maybe improve economics. As we can see, there is a lot of low-grade energy that is lost in the FlexSNG process that now is not valorized. So that could be an idea for an input, or maybe the CO2 stream. There is, well, without policy, there can't be much of a project. So the capital support, government capital support for de-risking projects, in my opinion, is necessary for these type of bioenergy projects. So yeah, that would be my short answer. I don't know if Paul is also an expert in this field, but.
Yeah, no, that's a perfect answer, Simone. I would just mimic what Tunet said in her presentation, that you need large volumes of biomass at a really low cost. You need a process that has good economies of scale so that as it gets big, it gets more economically interesting. With gasification, I think that's implicit to the technology, and you need a good policy to support whatever biovectors that you're going to make. And it's still not enough generally, even in the European context, to have a rate of return for a company in competition with other investment opportunities. And so this is kind of the dilemma, and thus industrial symbiosis. So the idea, and in particular, we could say that FlexSNG has a great opportunity for green chemicals. If we say that we can find the winning conditions, we can invest and implement. And then, of course, we have the rainy day when the policy sunsets, and now you've got a nice molecule that you're able to build on, albeit with limitations on all commodity products that would come from that. But you are de-risked to a large extent. So great question, Cedric, and no easy answer to that one, of course. Olivier asks, for energy as well as benefits, did you consider 100% recovery? Because there's a lot of loss as well as contaminants, e.g. sulfur, that could decrease the benefits of biogas. I would say yes, that it's been, the process, FlexSNG process, has been modeled very carefully based on the results of VTT, as Simone showed in that first presentation, in the methodology, and so it's quantitative for the set of conditions, design conditions that Simone has just shown. In terms of availability, your calculation considers all feedstock, or you apply a factor, because there's a lot of challenges for agricultural as forestry biomass today. Yes, of course, we do agree with that, Olivier, and VTT would be the best to answer that question. They ran the pilot trials there, and it could be that Mina has a comment to make, but certainly wood waste is the easiest to run in the process. And when we say in the process, I think the good folks from VTT would say they can run anything through the gasifier itself. The challenge is in the secret sauce, in the syngas cleanup, the plastics and the ash. So I'm sure, Mina, would you like to, you're just back, would you like to add something to that comment?
Well, you just said that the wood is the easiest one. Yes, it is, and then the waste wood is the difficult one, and especially if it contains some plastics or other impurities, the difficulties will be in the final gas cleaning section then. So that is in a brief. Yeah, thanks.
Thanks, Mina. And I'd also add the configurations that were looked at. FlexSNG, a big part of the innovation is that it has two modes of operation. And then there's a few configurations. And related to that is the production of biochar and then the re-injection of biochar, the mixing of biochar with some of the feedstocks. VTT showed that this really stabilized the operation to a good extent, even with difficult feedstocks. Okay, if there's another question, that would be great. Otherwise, I think I'll say thank you very much to our great speakers today. What a team, and all of the guests that are here online. And make a little plug for the final FlexSNG webinar, which is to be held next week. And there we're going to have summary presentations from each of the work packages across the project. So today focused on the breadth of systems engineering that we used. And next week is the overall project. So we hope to see you back then. Thank you very much.
Thank you, everyone. Have a nice
you.
day.
Thank you so much.
Thank you,
Bye.
everyone.
Bye-bye.